Okay, I want to talk about conservation of momentum. So conservation of momentum often includes objects either colliding together or like exploding and blasting apart, or a cannon shooting in one direction and the recoil in the opposite direction. But it's almost always involving two objects, right? And this is where Newton's law, third law, comes into play, action, reaction. The force on one object is going to equal and opposite the force on the other object. But what conservation of momentum says, and this is the only equation you'll see in the reference table, is momentum before equals momentum afterwards. So let's think about this, right? Before the collision, we have a 2 kilogram car. I'll make it a car, right? We'll put little wheels on it. That's going to collide with a 5 kilogram car. So momentum before the collision is going to be mass times velocity of this object plus the mass times the velocity of this object. 2 kilograms times 3 meters per second plus 5 kilograms times 0 meters per second. So you end up getting a total of 6 kilogram meters per second. This is 0, so that term goes away. So you know that after the collision, the total momentum is going to be 6 kilogram meters per second. Now, I have not yet given you enough information to tell you how to solve this. But let's say, for example, they stick together. You know that the total momentum is still 6 kilogram meters per second, and they are now stuck together. You're going to have a 2 kilogram and a 5 kilogram car. And because they're stuck together, they're basically one object moving at the same speed. So the mass times velocity has got to be constant. It's the same after as before. So it's still 6 kilogram meters per second. So you end up getting 6 kilogram meters per second is equal to the mass, the combined mass, 7 kilograms times the velocity. And you can then solve for velocity. It's just 6 divided by 7 kilogram meters per second divided by kilograms. Units cancel out, and you get 6 divided by 7, which is 0.86 meters per second. So by knowing the momentum before, we knew it was the same momentum as the momentum after, and we could solve for the velocity of the two cars that stuck together. Now let me give you an alternate scenario. Maybe they don't stick together. Maybe what we see is car 1, the 2 kilogram car, is going backwards at 1 meter per second. And car 2 is going forwards, the 5 kilogram car, at some unknown velocity. And we want to figure out what this velocity is. I'm not quite sure if the energy works out with this. I'm not going to worry about that now. Right now I'm just going to focus on conservation of momentum. So we know that the total momentum is still 6 kilogram meters per second, because that's what it was before the collision. So what is it afterwards? Well, the mass of car 1 is 2 kilograms. And the velocity of car 1 is now negative 1 meters per second. Because it's going backwards, it's going in the negative direction, so it needs to have a negative velocity. Plus the mass of car 2, 5 kilograms, times its velocity v. So you end up getting, going to ignore units just temporarily, 6 kilogram meters per second equals negative 2 plus 5v. So you end up getting 8 equals 5v, or v equals 8 fifths, which should be 1.4 meters per second. So car 2 is going at a speed faster than it was before, and momentum is still conserved. You got to ask yourself what's going on. I'm going to give you one last example, and this example is going to be of a cannon shooting a cannonball. And as you recall, I said objects, there's your cannon, shooting a cannonball. Boom, the cannonball goes out. Let's say it is a 5 kilogram cannonball and its velocity is 80 meters a second. It's going pretty quickly. And let's say your cannon here is 100 kilograms. So before they were shot, both objects were at rest. So this is not a collision, this is like an explosion. Sometimes you can have spring launches as well. So P total, which is M1 V1 plus M2 V2, is just 0 because both objects had a velocity of 0. So now let's go to afterwards. Afterwards, you still have 0 momentum. That's because the object's momentum going in each direction has got to be equal and opposite. So you have a 100 kilogram cannon going at some velocity, we don't know what that is, plus a 5 kilogram cannonball going at 80 meters per second. So you end up getting 0 equals 100 V plus 400. And so let's solve for V. 100 V equals negative 400. So V equals 400 divided by 1, negative sign there. So negative 4 meters per second is your velocity. So cannonball is going on at 80, and your cannon recoils, and in recoiling it's going 4 meters per second in the opposite direction, the negative direction to the left. One thing I want to point out is that through Newton's third law, we said that the force on these objects is equal and opposite, right? The force on this is equal and opposite to the force on that. But because they have different masses, they have different accelerations. The object with more mass should have a much smaller acceleration because acceleration is equal to net force divided by mass. So in this case, the massive object only has only comes out at 4 meters per second after the launch. This object comes out at 80 meters per second after the launch, which tells you that this must have had a much bigger acceleration than this did. And in fact, conservation of momentum, this whole thing comes out of Newton's second law, in large part, and Newton's third law, applying them. And you can tie them all in together along with impulse. I'm not going to get into it now. These are a couple basic momentum conservation problems. You're going to see some others as we go on. Thank you very much for watching.